Rosaly Lopes and its scientific achievements from the Cassini Titan radar mapper.
Thank you, and thank you to the organizers for asking me to give this talk, particularly since I was kind of a late addition to the Cassini team. So you have seen this iconic image of the North Polar region showing the lakes and seas. I'll go back to it a little later. But I want to start by telling you a story that was told to me by Latsi Roth, who was on the Cassini team. Back in 1980, when Voyager flew by, Latsi told me he was in Charles Elache's office, and at that time, they were planning to fly the first planetary radar to Venus that turned out to be the Magellan mission. And someone came along with a printout of that picture, and Charles looked at it and said, "That's our next target." So he was always a visionary. Anyway, Enrico introduced the radar and told you about the modes of the radar. So as we flew by Titan, I'll just remind you that depending on the altitude, we would change modes, and the mode that I became most interested in was SAR, because the SAR is what gives you the geology, and that's what I came into the team to do. But other than these modes, there are the ones that Steve Wall referred to as engineers get clever. So there is the high SAR. So you see here, maybe I can point, this is Minerva, that's the largest impact crater on Titan. And in the central part, we have Minerva with SAR, regular SAR, and then the background is with high SAR. So that is when we use SAR at higher altitudes. And the other clever mode is called SAR Topo, and Brian Stiles, one of our engineers, came up with that. And because the multiple antenna beams are used when you do SAR imaging, we can compare overlapping regions between the beams and estimate surface heights. It's not, of course, as good as altimetry, but it turned out to be quite useful, because at least when we were mapping the geology, we could see the relative difference in topography. Enrico told you about putting the radiometry mode into the Cassini, as part of the Cassini radar. And this turned out to be really useful for the geology. Here from Mike Johnson and Alice Legal was working with him, is an emissivity map, global map from radiometry. And the organic regions have this higher emissivity, while the more icy regions have this colder emissivity because of the way they scatter. And again, that was really useful when we were mapping the geology, because it would tell us differences between the different terrains. And here is a global map of the Titan topography done by Ralph Lorenz and others. Essentially by looking at taking the altimetry data and the SAR topo data and splicing it and making this global map. So with SAR, we did not get global coverage with SAR, but we got enough coverage at different latitudes and longitudes that we could actually have a good idea of the global geology, because these were well distributed in latitude and longitude. Our first SAR image, this is only part of it, But you can see it's actually quite difficult to interpret SAW from a geology point of view. But we could see that there were uh, uh, here channels and fans coming out of these channels, bright channels. And the radar wavelengths 2.3 centimeters. So the so-called brightness depends on the roughness of the terrain. There is a feature on the other side, which got the name of Ganesha Macula. We at first thought it was a volcanic region until we got topography and realized it was not a dome at all, even though everyone who looked at it, like an LPSC, said, oh yes, that's a volcanic dome. So in fact, topography is one of the most useful measurements you can have for geology. The radar data also help give the context for the Huygens landing site. You can see here that we could map these dunes from the DISA data to radar. So it helped to pinpoint the location of the Huygens landing. So I'm going to focus a little on the mapping because that's what I worked on. Have my timer here. So, as I said, with SAW, we did not get global coverage. So, in order to map the geology of the surface, we had to get clever too. And we used every available data set. We used, SAW, the ISS map done by Eric here, VIMS, SAW topo, topography, the emissivity map from Mike Johnson, so that we could primarily using the SAW, but correlate the areas where we had SAW with this other data so that we could use it to infer the geology from areas where we didn't have SAW. And so this is what we came up with, the geologic map of Titan. And as you can see, there is like a dichotomy. The lower latitudes have more of the mountainous terrain that we interpret as old crust, more icy. The purple are dunes, so the dunes again concentrate at lower latitudes. The lakes, of course, as we already seen, are at the polar latitudes primarily, the north polar regions. And most of Titan are plains, in fact, made up of organic material and probably largely deposited by wind. And here we have the percentage of various units. And I'm going to go through them a bit. So dunes on Titan, at first in the first images of the dunes, we didn't know what they were and we nicknamed them cat scratches. And then, in fact, Ralph Lorenz wrote the first paper on dunes when we saw that they diverted around topographic highs, which are the mountainous materials, this bright material. In ISS and VIMS, they also had, a darker color. And here from Janie Radebo, comparison with dunes on Egypt. And this type of dunes is what we call longitudinal dunes on Earth. Most dunes on Earth are Balkans, and that's when they form perpendicular to the direction of wind. But these ones form when wind comes primarily from two directions. And these dunes can become very, very long, hundreds of kilometers long. Impact craters, there are not many impact craters on Titan, indicating that the surface is actually quite young. Chuck Wood did the first paper on craters. And the age is between 200 million years up to 1 billion years. And these are some of the craters on Titan. As a bit of an aside, I then, after Cassini did a project on the astrobiology of Titan with a bunch of other people, we think that the most likely place for life to have developed on Titan is in the oceans, and particularly if organic material could come from the surface into the ocean. And so a question was, what could cause that? Could a large impact like Minerva, cause this mixing? And working with a scientist, in fact, from Brazil, we found that yes, this mixing could occur with a sufficiently large impact. There are also rivers on Titan, and some of them contain liquid. That was work by also Ralph and Valerio Poggiali. Karst-like terrain. Mike Malaska did a lot of the work on karst, heavily eroded incised regions. And I know I have to go fast. Mountains. These are some of the mountain ridges on Titan, indicating that Titan has tectonics, and lakes that you have heard a lot about already. So, but I'll just say that we were looking for them, and this was the most, I think, exciting discovery from the Cassini radar. Seas, in fact, some of these lakes were so large that we got permission from the IAU to refer to them as mares or seas. And here again is the iconic mosaic. Steve Wall liked to joke that we just missed Santa Claus house. We did not get the North Pole. We also have heard about the bathymetry and the spectacular work of Marco Mastro Giuseppe, who in fact is here, and they're in the back. And this is something that we never thought that we could do, and it was a great and wonderful surprise when Marco showed us his work. And Marco and Alex Hayes and others did here is the bathymetry of Ligeia Mare. And this is possible because the methane and ethane is so transparent to the radar. So the deepest points here are about 200 meters. Just a moment to talk about the Magic Island. That was a nice mystery. Between two flybys, we noticed that something had changed on the edge of Ligeia Mare, and then in a later flyby, it also changed. The engineers spent a lot of time showing this was not an artifact. And Jonathan's student, Jason Hofgartner, wrote a couple of papers on it. We're still not sure exactly what it is. Here are some of the possible explanations, but we're sure it's not an island and it's not magic. So I was very interested in looking for cryovolcanoes, and in fact, we did find particularly one region that looked and saw like a cryovolcano. I'm going to point it out here. And it turned out to be a deep pit next to a very tall mountain. The pit is about 1 kilometer deep. And Randy Kirk and others at the USGS got even more clever because of two overlapping passes, and they were able to do a kind of stereo, which is what you see here. And this is just to show that this feature in purple there, Sotra, is not an impact crater. It is a collapse feature. And there is a flyover that I don't think I have time to show, but I am going to, end by saying that Titan is called the Earth of the outer solar system because it has the geologic processes that the Earth has, endogenic processes, tectonism and volcanism, and then the exogenic, like erosion and impact cratering. So, you know, Titan is indeed the Earth of the outer solar system. And I'll just give a plug for our COSPAR book that several of you here are lead authors or co-authors. And it came out this year. So thank you very much.
Questions? I will start with the first question then.
Okay.
So when the radar was first selected, there were skeptics in the community who argued that volume scattering would be dominant in Titan's surface and we would be unable to interpret the radar images in terms of geologic features. That, of course, has not turned out to be the case, but there is volume scattering. And do you want to comment a little bit on what that means and what the challenges are?
For someone who had never worked with radar before, interpreting the radar data of the surface was actually quite a challenge. And after a while, because you know, sometimes things look in the radar and there are the scattering effects, and sometimes you even think that you saw a change from one flyby to the other, and then you ask the real experts and they go like, no, it isn't. So the Magic Island was, you know, actually one that we, after a lot of work on the part of the engineers, we could make sure that was, you know, not an artifact. But as I said, the data from other experiments also helped a lot. We did a lot of correlation with ISS images and VIMs, and even though they suffered from their own effects, when you're actually putting it all together, it really helped a lot. And the topography also helped a lot. You know, I have a colleague who says that if she had to choose one data set to interpret geology, she would choose altimetry or topography.
Another question. So I will, while you're thinking up your question, I will make the comment that this was a very difficult experiment, in part because Titan's atmosphere meant the spacecraft had to be quite a ways away from Titan. And of course, radar, the signal goes off as r to the fourth, not r squared, because you have the transmitted and the received signal. Yeah. And so this was extremely challenging from the signal to noise point of view. And so it was really quite an achievement.
And in fact, the highest resolution we have is about 350 meters, which again is very challenging when you're trying to interpret geology. You have a question?
I don't know much about radar. I understand that it provides black and white images, but the brightness is not related to the real surface brightness, but rather an indication of roughness.
Yes.
Now, these iconic images of the lakes, there's some color involved. The solid surface is brownish, the lakes are dark blue. How does this color come about?
Okay, no, those images are colorized, of course, but what we could tell with the radar is that at the radar wavelength, 2.3 centimeters, the surface was very flat. We could, in fact, ISS had detected, had seen a lake in the southern hemisphere, but they weren't sure it was a lake because it looked like a lake, but it could just be a dark, flawed region. And but these lakes, to have a series of them so smooth, so flat to radar, it really the most obvious conclusion was that they were lakes. And then VIMS detected a glint from one of the lakes, and that confirmed it even more. And then when Marco was able to do the bathymetry, then we knew even more. We were even more sure.
I mean, I couldn't have imagined that there'd be multiple ways to determine that these were liquids, but Cassini did have multiple ways
Yes,
to do it.
yeah,
So
we did, which
it's a
again-
slam dunk, no pun intended.
Yeah, it shows the value of several data sets.
All right, well, let's thank Rosaly again.